chapter 1, basically we're talking about, the idea of what a parameter. We talked about, sample, right? And then in chapter, we basically classify the data. Classify what type of data it is. And chapter 3, we'll be classifying and choosing which is the best data to use from our sample, obviously. And then we have central tendencies. Central tendencies. And then we have, as part of the central tendencies, we have here too, they start to bridge here a little bit, but we're starting to organize the data too. So central tendencies would be like the standard deviation, right? Or the sample mean, right? And then we have histogram, kind of to help us figure out what type of distribution we're using. Remember, we're looking for patterns in the data to help us do what? Prediction, right? Or test a hypothesis. So we started broaching that, and then over here on these graphs, you have your histograph, you have your histogram, right? And one thing that we had something where we just did a count, like a dot plot or what we call a frequency plot, where we decide what cells to divide it from, 0 to 1 or 2, whatever, 3. And then we count how many observations fall in here. Do you remember? This would be a frequency count. But if you take your total sample size, which is n, right, and you divide it into each thing, then you get a percentage for your histogram. That will be no bigger than 1%, right? 100. I mean, these are probabilities. Okay. And there's another one, there's a bunch of them, stem and leaf. It's like a stem, and then those are the leaves coming off of it. And then we have a scatter plot, which when you had two variables, you wanted to compare them, so variable x and y. These are random variables in the sense that they're coming from a random process that has structure. And we look at this thing. Ooh. And we had some concept here called R, which was the correlation coefficient. Okay? And so that's basically where we're headed. I mean, you can see we're going towards hypothesis testing and forecasting. These are just mechanisms by which we... So, and with regards to the tendency, the most important thing that I keep trying to I mean, this is mechanical, but really, what I really want you to see is that, we're talking about in the population, we have mu, which is a mean. Another word means average. Okay? And we have this thing here, you call it, that one probably wouldn't be it, that would be, that's going to be, so this is there are two words for this. One's called a deviation. And the deviation has this squared. And the only difference is that you're going to have a square root or not. And then we also have what in the population, this is under the population category. This which we most often don't know about, that we want to forecast about. Okay? I don't know why I need this, huh? Okay. So let's see. Let me clear up some a little bit. All right. Oh, this correlation coefficient, by the way, tells you how tightly, if they're moving in some direction, and how tightly bundled they are together, like if they're correlated or not, right? I told you I did a little thing myself. It was people who eat pizza crust make their beds. There was a correlation. That doesn't mean that pizza causes you not to make your bed, but it doesn't show causality. The cigarette companies for a long time said would fight having to put any warnings on their product, because even though there was a very strong correlation between smoking and getting lung cancer, but the actual mechanism by which it happens hadn't been explained yet. So they kept saying, well, it's correlated, but that doesn't mean it actually causes it, But, okay. Now let me just clean it up. Okay, so I'm going to be plummeting this into your brain. We got the population, we got the sample, right? We're going to use a sample to make inferences about the population. That's the whole big picture, really. And in this population that we have the mu that we just talked about, right? And that was a summation of all the observations from I equals 1 to capital N. And the one we used in our sample, actually I could do the sample in green, huh? We'll call it X bar. That's the summation of all these observations in our sample, not the population. And so I goes from equals to 1 to little n, which this will be our best predictor for this. Okay, y'all got it at the same time? How about this? That's the population deviation. And it deviates from the mean, doesn't it? Oops, I'll do that in black. This is lowercase sigma. Okay, and that is going to take the summation of, in parentheses, each observation, but you're going to subtract the mu, this guy, squared, and you're going to divide by capital N. You see that? So now let's go to the best estimator of it, which is going to be our sample deviation. Okay, so you can see what happens here. If I want, I call it variance. Variance would be just without the squared. Okay, so it would be this. Squared, and then I have divided by n. So I just square rooted both sides. But this then will be like the deviation. It's the same number, really. I mean, just they've been square rooted. So here we have the variance. It's like same thing. So what we do is this. And now we take every observation, and it's true, we subtract. What do we subtract from it? What did I do here? It should give you kind of a hint. Yeah. Yeah. This time we set the sample mean, not mu. And we don't want negative values, so we square it. And it turns out we divide this by n minus 1. Okay, and it turns out there's a shortcut. This makes more sense to me. The shortcut's easier to calculate by hand or whatever, but it's not as intuitive. So this can be rewritten as this. So you're going to have summation of xi. Okay, now they want each one of these guys squared and then added. Each observation squared and then added. Okay, and I'm going to multiply by n here, and then I'm going to subtract this guy. Now this is a little different. I want you to add up all the observations, see, from 1 to little n, right? Because this is our sample. So I equals 1 to little n, true? And now I'm going to divide by n times n minus 1. It's supposed to be easier because, okay, now look what's happening here. Okay, now, oh wait, I mean, this thing here is, this whole thing here is squared. Okay, so this is basically adding up all of your observations, add them all up, and square it. And this is just take each observation as you're adding it and square it. You see the difference? No? You see what I'm saying? That this actually, what does this mean? Okay, so I'll just spread it out a bit. You still have n as your sample size, But this guy, the summation, if I get rid of the summation and put it in terms of addition, I'll just x of 1 plus x of 2, right? Plus dot, 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 and the nth observation. That's what that means. But it says square each one first, right? Now, I'm finished with that, and then I come minus. Here's the minus sign. And what does this mean? Well, this means x1 plus x2 plus dot, dot, dot plus x of n, that quantity squared. Well, and then I have to close the parentheses here. You see, I ran out of space. This one here. And then I divide this by n times n minus 1. Okay, now, this is not too hard to work out. I mean, this is a little different because you have to take each, this is saying this, right? If I add up, it means I got to take x1 minus x bar squared plus x2 minus x bar squared plus dot, dot, dot plus, right, the last term, the nth term, right, subtract that and then square that. See, and then you divide that by n minus 1. That's what this means without the summation signs. I hope you begin to see how convenient this is after a while, because I don't have to do that each time. That's what that means, the summation sign. It kind of looks cool too, huh? Like a genius or something, right? Like Einstein or something. No? Well, it looks good. And then finally here on the population, we have what we call our distribution. This one, for example, would be a chi-square distribution, and it's skewed to the left. It's called skewness. This is called chi-squared, chi. And then, of course, we have a bell curve, which is what we call our normal. We call it a bell, right? Or because it looks like a bell. It's probably the most used of all. Many biological things have fall into the herd mentality, where most of the thing is grouped around the mean. We don't take too much chances. Those who do take chances either get killed off or get very rich. And there are two types here. Remember, this particular one I draw is called a continuous distribution, because there's you imagine if you're trying to do a gradation on eye color. Well, how many different eye colors are there, right? In essence, there's an infinite band between between what the human eye can perceive as light. But even within that, the amount of variation in between depends only on how discriminate you are between one shade of gray or another, or green, right? So that is an example of a continuous distribution. Whereas if you want to see if some dice are fair, and you keep rolling and rolling and rolling and see where the observations, this, if it's a fair dice, oops, and let me know just right where I was writing. How's that for service? Come on. See if it works. Oh, that's good. So in this case, remember, have like your histogram where it goes from you can have all the way up to 1. So you can have 0.9, 0.8, these are probabilities, down to 0. And of course, this is number 1, 2, 3, 4, 5, 6, right? Obviously, these will never have in between. They'll all be the same probability if it's fair, right? So this is a case of a discrete. Right, distribution. Okay? Is it okay? I can't tell. You got your computers out, and it sounds like you're in deep thought. Okay. And by the way, what is the shape of that? Well, we call this particular distribution a uniform distribution. Now, you don't see it yet, but we'll be using this now to make predictions based on where our test statistics lands. We're going to have certain cutoffs, and if the test statistics lands on this side, we're going to reject the hypothesis. And if it lands in here, we will accept. Okay? That's where we're headed. You like green or not? No? Oh. So you mean it doesn't matter? Do you know as it gets dark, we all get colorblind? So we share your pain. When we, as the light gets lower and lower, there's not enough reflective things that trigger the color receptors in our eyes, so we're all see like dogs, like a gray, until it's completely on, and then you don't see anything as you're blind as bad. But yeah, right there, you start losing color at nighttime, if you notice. Go outside at night and look and see what colors things are. So don't feel alone. Although they got these glasses now, I heard. Have you seen those? Where they're really expensive and they do mess your eyes up. They mess your eyes or your brain? They're not perfect. Nothing really. And I'd like to meet something perfect, but they show these YouTube things where these guys, they give them this thing, like these, and they first time they see color. Of course, people are wearing all sorts of bright colors and stuff. And they're in shock. Almost like it can't be that. Is that for real? That's almost fake cartoonish colors. Anyhow, that's something different. Okay, any questions on this? I did that, didn't I? No? Is it too easy? The summations don't have you freaked out? You like summations? Go show your boyfriend or husband stuff. They'll be amazed. Like, wow, you must be really smart. That's what I like about math. He got everybody fooled. Let's see. Okay. All right. So now, the next section was classifying, and I don't want to do it. You can do it. It's but whether it's, what type of data it is. You can. The homework will help you. So, okay. So basically, I really covered pretty good. Chapter 1, anyway, with regards to sample and parameter, right? And then you read about classifying the different types of data. And then we have the central tendencies, which is chapter 3, actually. No, it's 2.1. Chapter 2 has got the, my mistake. Chapter 2 is the idea that of all those equations I drew. That's it. So there's one other thing. I don't know that you'll use it too much, but you can also calculate the standard deviation and the mean from a frequency graph. So let's do that. So with a frequency graph, you're going to have just counts. 3, 5, 7, 3, like this, right? That is a frequency graph. Okay, but here, so total sample size n is equal to 18, right? But you don't really know what the raw data is. If you're given this, you don't know. Somebody counted and put them into these categories. So, but if you're given it in this sense, you can still calculate something close to the average. So this would be like the frequency of the first cell and the frequency of the second, the frequency of the third, and the frequency of the fourth, right? So one way of doing that would be to do the, if you recall, okay, so we got this, right, our sample average, right? Do you remember, you can't forget this, right? It's each observation from I equals 1 to little n divided by n, right? But one way you could rewrite that, if you're going to do the sample, and I'm going to put a little f here, meaning it's for average from a relative frequency graph. Yeah. Okay, in that sense, then this becomes the summation of, now f going from I, because there's f1, 2, 3, 4. So that'd be 4, right? And then I have, fi, let's see, yeah, fi, and then we have this different kind of xi. This is, I'm going to put a little bar here, no, maybe a little hat, because I'm actually, well, if I'm between here and here, my x guy in this case is like the midpoint of those. So it's the same, it's the midpoint of every one of these. This now becomes, each one of those becomes x hat, you know what I'm saying? Because you don't know the raw data. So you find how many group in there between this range and this range, right? These are the x values in here. A little different than this, because this is the raw data. And this is this thing here. So then you take this, and you divide that by what? The summation of all the frequencies. And what's another way of saying that? Well, you know what happened when I added up all my frequencies? I got, what, 18? Yeah? That's actually ends up being, another way of saying a sample size, which we do have. Okay? That's just a little bit esoteric. You only need that when you're actually given a graph and they ask you to find the average. So what does that actually look like? It looks like this. Let's expand it. We go to 1 first. So I want f of 1, which is this number 3, right? And then whatever that would be, like a half plus, and then you go f of 2, right? And then that'd be like, oh, what, 1.5? Which number? Oh, when you decide where these widths are at. So these guys are like, what I'm trying to get at is that this midpoint is the different x hats. You're really taking an average, right, of each one of those shell blocks and counting that as your x. Okay? And then this would go, this is like 1.5, right? And so on until you stop. Your counter stops, right? Because you've hit, whatever the fourth one is, and that would be your f of, that's the fourth one, right? And then that one, whatever it is, you get the idea of like 3.5 or whatever. Okay, and then this is going to be divided by this. Well, what does this mean? This means just f1 plus f2 plus ... fn. Okay. If you can get a gist of what I'm doing, it's good. You don't have to learn how to do the algebra of this. I'm not going to have you. It's not really worth it. I mean, I can prove by how one goes into the other, but I don't want to mess with your brains. What? Like what? Hieroglyphs. Oh, is it? I want you to be able to interpret hieroglyphics, and I guess it does. Yeah, I'll do some examples so that you can get some feel. Yeah, well, this is the actual number, but I understand what you're saying. I'll do it on the computer, on the software when I show you how to do it. Okay, it's good. No, I know when I went through math, I suffered like that too. Just give me an example, would you? I don't want to know how it works. I want to know examples so I can follow it, and then I just copy the example, and then like a dodo bird, just do what you see and do it. Yeah.
I just mean like, you're putting the formulas there, right?
Mm-hmm.
Yes, I've been gone. I told this.
Oh, well, that's even worse. But that's okay. I understand your point, though, I think.
It was an
Oh.
example rather than just like a formula.
Yeah, and this ends up being an
Example.
right. Well, what I was saying was that even though it doesn't look so pleasing, I like, of course, it looks like poetry to me, but it's good to push you a little bit in this direction, the theory. It actually helps in the end because it'll start to kind of sink in from the back. Okay, but that was it, except for we had one like this too. Remember that we had this one from our sample, our deviation, do you remember? Our variance. It says, yeah, well, that was what? Take each observation. This kind of makes intuitive sense, see? And then square that, right? And then we divide this by n minus 1. Okay, and I showed you there was another way of writing it. I don't bother, but there's another way of doing this too. So instead of, so what I'll have is, I'll have an equation where, well, if I do that equation, you'll really freak out. It's a longer one. But I'll let you look at it then. I guess it's the same idea, but we do, oh, this is, okay. All right, well, we'll work our ways with, we'll do some examples. I know that people want to see examples, but I just kind of giving you the idea of the central mean.
This is like what happens like inside StatCrunch.
What?
This is what happens inside StatCrunch.
Yeah, somebody wrote the programs.
Right.
And that's called numerical analysis. Is and you go, if you want to go into math and you want to go into like applied mathematics, the people who build StatCrunch are taking degrees in what's called numerical analysis. They're very good thing to have because almost everybody wants an engineer that's numerical analysis. Even though you have software packages like StatCrunch, you always have it that you have to be like modified a bit or adjusted, fine-tuned. It's like people who can do C++, or it might help with, okay, let me get rid of that. Okay, now we go on to, let's try some examples here. First, let me show the book. Yeah, let's try that, if that works. Let's see if I go back on again. Okay. Okay. That's weird. Don't show me that again. Maybe it doesn't work in Chrome. Okay. Is it working?
Try clicking e-text.
Clicking it?
Like the highlighted e-text. Maybe. Right.
Oh, up there?
Nope.
Oh.
Right in the middle.
Right in the middle?
Right to the right of the logo.
Oh, here, yeah. Thanks. Sometimes you're blind without knowing it. You're blindly, oh. Okay. All right. Okay, so let's see. Let's just go through here. There's got to be a faster way. I don't want to know about the author right now. Okay, here we go. It doesn't show it, but this is the parameter and the samples, right? And then the types of data, and then collecting the data. Then the frequency of them falling in individual cells and graphing of that. One type is called a scatter plot. It doesn't really belong here, this section here, but they threw it in there. Scatter plot is, when you're comparing two variables and you're graphing where they meet. And this correlation is how tight that scatter plot is around a tendency. If you have something that's just thrown on the board, that's random. The R will be almost 0, right? Because it goes from -1 to 1. Why minus and positive? Why doesn't it just go from 0 to 1? Why would it go from -1 to 0 anyway? No? That is kind of weird. But basically, you have it like if the graph is here, the scatter graph's going like this, right? From your perspective, if you drew a line through it, that has a positive slope. So the sign is the direction of the slope of a line going through. And the higher you're closer to 1, the tighter the dots are to that line. But you could have a negative slope too, right? Instead of going like that, it could be going like this. I'm trying to look at it from here, saying, yeah, that's negative, right? Okay. And now, measures of center. That's X bar, right? X bar, in the population, it was mu. The variation, in the population, it was sigma squared, but it's S squared for sample variation. You understand? Variance or deviation is the same thing. It's just whether it's squared or not, okay? And now they got this thing called box plots, which is pretty cool. I like box plots. I use it a lot on the stock market because it'll show a lot in a little. Let me show you. Okay, and now just to give you a little more excitement in the probability, we have to learn certain rules of probability, how to calculate it. With this much, then we start getting into our individual distributions. Normal, the bell curve. A discrete, like throwing the dice, right? And then the big one is hypothesis testing, okay? Now, this chapter here, 7, is a bit, it's going to be comparing like 2 different populations, the differences between observations, okay? But in the end, we want, here's making inferences. Inferences is like doing a forecast. You're making an inference based on the data. So we have 2 different means from 2 different samples, and independent means that one sample is not affecting the other, right? These are just different tests to keep being able to forecast depending on the type of data that we're using. That gives you kind of a rundown. And here again now, they came back. You see when I said it didn't really belong there, the correlation and regression? Now, this is more in-depth. So basic for me, I mean, the last chapter 9 really, if that's what it was, is really what the course is about. These are, regression is that putting the line through the dots, and here's prediction, interval, and variation. But the rest of these are like for quality control, like goodness of fit, analysis of variance. You know that we can look at an average, right? And I can say here an average, and you can compare an average to some other average, right? Your average grade with another average grade, okay? But if you compare your grade with somebody in another class, taking the same class, and you compare it to them, right? We have to look at the variance. Now we're worried about the variance because we can't just, it could be from the grades are spread differently from one classroom to the other. So if you don't take account variance, then it's like I told you with the bank account. You ask what is the average bank deposit? So it could be skewed by having an outlier way far out. So just looking at the average might give you a false sense of, yeah, we're really doing better. Our average has gone up. My question to them is that, well, what happened to your variance? Is this right? Because the variance is so huge. IQ, for example, IQ tests are are controversial because they use them to, well, they use it a lot. I mean, in one form or another, maybe even to which school you get into or how you're tracked as a kid even. They'll start tracking you, and it's unfortunately, if they think you're not on track, they put you in this track where they don't expect much out of you. But IQ, across ethnics, like if you take on average, like blacks, and you take, say, Hispanics, whites, Asians, I don't call them different race. They're not a different race. It's a different ethnicity. It's a cultural thing. You know, every group of people have had a strong chromosome kind of a distribution because they've been, so you have certain physical differences, but with regards to the plasticity of the brain, it's been shown that it's pretty robust. So when they did a thing called eugenics, I don't know if you're familiar with it or not, back in not too far last century, early last century, they tried to do phrenology where they measured parts of your head, your nose, your head, your skull, especially, you know, the Nazis were big on it. And they were trying to show that, you know, the Aryan was like superior in all ways, and they were trying to prove it even with measuring like the distance between the eyes and the jaw, and like, you know, anyhow. But when the IQ came in, which is a ratio of the grade you get on a test divided by your age. Okay, so they tried to show that, you know, minorities in particular, like blacks and darker people in general, are you know, have a lower IQ, which was, yeah, it's okay. And here's what happened. It turns out, like, so they gave the IQ test, right? And sure enough, some ethnics lower than the other. Like in general, let's say that in general, of course, in terms of African American or African period, their IQ seemed to be on average lower than it was with the Caucasian. All right. Now, keep in mind the Caucasian wrote the test. Okay. So then they went to the Asian, right? In general, the Asian, and they were scoring higher than the Caucasian. Okay, so that was that was a real blow for eugenics, because their whole thing was going towards showing that, you know, the white Aryan was a superior race. And it turns out that, you know, but here's the thing: if you analyze the data and you see where the IQ is hitting among ethnicities, right? The question is the variance. So the variance is actually the same in all groups. So within their mean, right, the way they vary off the mean is the same. So combined with the average and the variance, what is it telling you? It's telling you what you got here is cultural differences of a way maybe a test is viewed. Not hardball intelligence, but you know, even kids from an inner city, and you know, compared to you know, for example, they don't. You have people that are in the hood who you know, they never heard the word cul-de-sac. That's a French word, cul-de-sac, which is, you know, for some people live in a suburbia, it's pretty common. You go and split dead end and there's a circle, right? So a lot of it is, so what I'm showing you is an example of where you have to take into account the average and the variance to get a bigger picture, particularly if you're going to forecast. Okay. So so it's not too bad. Let's see. There must be a way to go like ahead, isn't there? There we go. Well, this is cool. So we were talking about exploring the data. Does that work? Oh. Okay. Describe. That was probability. So we did it move? Doesn't it move?
Expanded down.
Did it?
Yeah.
Oh, I
Well, on your screen.
it was so fast. I didn't even.
Yeah. So when you, yeah. When you
No, did that change?
No.
Oh, that's what I want.
You have to select another. So chapter 2, and then it gave you a list,
Oh yeah.
and then
Okay. So good. So you're an expert. So here we go. We got this in. Okay, this is determining how. Here's the frequency distribution, right? But you really have to determine the cell width So you can see how it can help lie with it, because if you take the data and you only make two categories, you can make it look like, yeah, this is way up in here and this is way down, right? Or if you have too finely described, you'll have gaps in your histogram. No, or yeah? Okay. So this is how you take your class limits. You take the lowest and the high, and you divide by how many limits you want. It'll give you the width of each cell. Okay? And a lot of this stat crunch takes care of it. And okay, so this is when you want to establish in your cells a little stopgap that'll force you to decide whether to put the observation on this side or this side. Did you see what they did with between 124 and 125? They have a barrier there. It's 124.5, right? So hopefully you'll know that it either lands in one cell or the other. All right? Bring it down. Not that. This is a good way to go through the book, huh? Fast. There's the maximum data. There's the minimum data point. That's the number of classes that you want. The number of cells, right? In this case, each cell is rounded up to 50. You just have to play with it. It's not that bad. Okay, now we have the relative frequency. Remember I was telling you. Relative frequency, you take each class, the number of observations that fell in that class. You understand what I mean by class? In a histogram, each one of those bars is a class. Right? And you divide it by the total observations, the total frequencies, right? Which really is your sample size. Right? And you divide it and you multiply by 100 to get a percentage. And now, I spoke about this before, the cumulative distribution. In this case, you keep adding up all the distributions, so it has to add up to 100. Probably better to see it as a graph. Let's see if they have it. Okay, so if you look at this, where the observations landed, notice how it's 2, 8, 38, and 2, the relative frequency, right? But already, you look at it, if you turn it this way, it already looking kind of normal, isn't it? Like a bell curve. No? Exciting? No? Okay. Well, it will be. Okay. And then let's go on. Huh? Talking about what? Oh, I'll go back. Okay, here. So if you were to set up a cell horizontally, right, you'd be somewhere between one cell from 75 to 124 and another one, right? But look at the frequency. Most of them are towards the middle. So that's actually a bell curve on the side. So it helps us. Yeah, I know. Well, that's why I get the big bucks, I guess. Comparing McDonald's and Dunkin' Donuts. Let's see. Make sure I don't have it right here. Okay. So these are frequencies, right? See them? And then these are probabilities, because we divided each one of this by the total number of frequencies. Okay, so it changes from relative to the histogram. What's next?
What's being compared?
Huh?
What was being compared in that?
In that particular problem?
Yeah.
Weight of pennies. That one is. So. Oh yeah, that's the important one, huh? Depends how long you want to live. So it's comparing the times to be serviced by the time you go up to a window and you get your order. So so these are the number of seconds. Dunkin' Donuts has that. That's what I was telling you. When you're doing a problem that has to show you, these are not giving you the raw data, but it's giving you the relative frequency.
Yeah, exactly. The raw data would be like going up there.
No, it's not raw either, because you don't know. These are all 18 groups that fell into that range. You don't know what exactly the data, because somebody already counted and grouped it up. Say, if I tell you I got 18 here, I got 18 between here and here. Okay, tell me what they are. You don't know.
Oh, meaning like it could be any
Yes, that's right. Yeah. That's why it's called a frequency.
I see.
So they're not giving, that's why I'm trying to say to the raw data,
Raw data would be exact.
that's when you use the formula where xi minus x bar, right, whatever. But if you don't have it, then you have a f. You'll see f in there, which is because you don't have the raw data anymore, you have the frequency. Okay. More of the same stuff. Okay, problems. And I'll get to the homework here in a second. Okay, now we have the histogram. It's just the relative frequency divided by each cell by the sample size, and then you make a scale from 0 to 100% or 0 to 1. That's it. We'll do those two. Okay, now here's kind of what I was telling you about. This is lunchtime service, right? Okay. So this is frequency. You see on the y-axis? Frequency is how many observations fell in each cell. Yes or no?
So that
Okay.
should be in tally, so.
Yeah. And you can find the deviation and the sample mean from the tally numbers instead of the order. So yeah. So here was like, so what's the difference between here and here? Actually, they look the same, don't they? Don't they? And they're even red. I'm not, unless you're colorblind, I don't know. Now, look at the numbers. 5, 10, 15, 20, right? Now look how the numbers have changed now. They've gone from 0 to right up to here is that's 50%. And the summations of all of these cannot be more than 100%. It's exciting. That would wake me up right there. Okay. So this is the histogram. This is the relative frequency. I try to make it harder, and I can't. Okay. Now, after you do your histogram, somebody tell me, what is the purpose of the histogram? Why did we do a histogram? From what? The sample, yes? Why? Why do we care? What are we trying to predict? I guess it's hard to get that concept over because, let me go back to here. Okay.
Well, it gives you the visual of the data. Right?
Yeah, it gives you a visual of the data, and what good is that?
It helps you in analyzing, right?
Yeah, oh, look at that. Did I write that? Yeah, cool. Okay. All right. So anyway, you saw that when you calculate your average, we call it x bar, from the sample, you're going to take every observation that you've taken in your sample, and you divide by n, right? But if it's in this categorical thing, relative frequency, yeah, then it changes to this. And you have xi. I put like a little hat, I don't remember, and then you have fi. Fi is the count on each cell. First cell, second cell, I equals 1 to the whatever cell. You understand? And then you divide. Now here we divided by n, right? Here we divide by the summation of just all the frequencies. And I'm saying that this is another way of saying n, because you're just adding up all your frequencies. Okay? Now, so why do we care about x bar? Because x bar in any form, whether it's from frequency or whether it's from the raw data, all of it's going to predict mu of the population, right? It's the same over and over. I'm just trying to beat it over your head till you get it, even if you don't, even if it looks like Greek, because it is. That is actually Greek, summation. Summation is Greek. You'll see it in the university. They have the Chi Sigma clubs, sororities. And anyhow, you know, we have the same setup for the population variance, right? This one, by the way, you know, was a summation of each observation from the population minus mu. Oh no, this is mu. I did that again. This each observation from the population. So it goes over every I. I don't really need this. Okay, but it goes from I equals 1 to capital N. It's still just an. That's what we were looking at. Anyhow, so to estimate this, we use this with little n. Okay? All right, that's okay. And this should be okay too, because the sigma is equal to let's see. Yeah, that's going to be okay, do it again. Where's the little guy? A reflection here. Okay, so that's going to be equal to summation, right? And over the whole population to capital N. Yes? And you're going to take every single observation and you're going to subtract the average. But the average for the population is mu, not x bar. We don't know this usually because the population is too large. So we use, what do we use? S squared, yes? Somebody say yeah. Okay? And what we did? We did something, there's several ways of representing it, but it was basically you take the sample average and you square it, add them all up, and this just goes from n minus 1, little n, see? Now, what I'm trying to show you is now the third branch of prediction, which is important. I don't know whether this is still Greek to you or not, but you have the concept is you're using your sample to get these morsels that will be used to predict population morsels. Okay? So the third leg that you have to understand is, and what the question I was asking you is, why do we use the histogram? Because it's true that it gives us an idea of the shape of the true distribution from which the phenomena is being produced. Right? You understand what I'm saying? Are you sure? You have to have a prediction for the true population mu, which is x bar. You have to have a true population for the sigma squared variance, which is s, sample deviation. Yeah? And you want to know from what kind of data, because something's, is it uniformed? Is it Bell? Is it chi? That's what this is about. These are distributions of your sample, not the population, right? Because you'd like to know. It's telling you, this distribution is telling you that yes, it's a random variable, but it's not 100% random because it's coming from some kind of process that's generating a bell curve. So if you know this, right, and you know these little morsel things, you've got some stuff to work with about making prediction in the future or whatever, hypothesis testing. Understand? So we're not just doing it for the fun of it. We're not doing it just to look at it. We're looking at it because it too is going to be the predictor of a true distribution of the population. You have to get that part, because if you don't, you're going to miss the whole course. The whole course is about prediction. And a lot of people, they never tie it together. They just, okay, how do you do a histogram? Okay, this is how. I'll give you an example. Oh, okay, I can do histogram. How you do this? Okay, but they don't see what it's all pointing towards. That's what makes stats hard, is to figure out what the hell is it for. Okay. Let's see. All right, so this looks like it's a good thing about a bell curve distribution. This is coming from a uniform distribution. This is coming from a skewed. Skewed means pushed over to the left, split over the right. A lot of times those are called a chi-square distribution. Okay. Why? Because we want to know something about the population, which we don't know. This to me is a scientific, mathematical way of going to see palm reader. You go down the highway and you say, $10, $15, stop by and we'll tell you whether you're going to be married happily or not. And believe it or not, the lady or whoever's operating on the other side has a lot of experience talking to people as they come in. First of all, you came in. So that means you want to know something about something's wrong. If it was perfect, you'd never come in, right? And then they're taking data off of what you're saying and what you look like. And then they're making these predictions, right? That's statistics, except for the fact that this is based on science, on mathematical rigor. But it's still probabilistic, meaning it's not never come out like most math classes that you're operating on it and you say, okay, I like math because you're going to have an answer. Solve for x. X equals this, right? Well, this is a little different. X equals this with a probability of being correct. No or yes? Yes or no? Are you sure? Okay. All right, now next. Oh, I just painted it. Now, in StatCrunch, after you've done your histogram, you can overlay what would be an idealistic bell curve, see? So this is the rough data from the sample. This would be what we perceive the population distribution to be. Yes? Is it okay? You? Yeah? Okay. I'm not sure what the toes are about, but they look clean. Let's see. Skewness resembles toes on the left foot. What the hell? Well, I don't know. I'm not going to mess with that. Okay. Now we come to quartiles. Okay. Do you recall how we calculate the median? So let's see. Let me give you an example, because I know you want examples. And there's let's do a quick. See, well, it let me write on here. I don't know, did it? Yeah. Okay. So hey, that's pretty cool. So let's say you have the data. Here's the data. 2, 6. I know you want numbers. 7, 8, 9, 9, and 11. Okay, whatever, I don't know, I'll find it. I don't know what it's about. But anyway, there's the data, okay? I talked to you about the mean, right? What would you do to the mean? You would add each observation up, total, and divide by n, which n in this case is what? 7? Okay? So those formulas that I'm telling you would be exactly this. You'd add that. And as a matter of fact, I equals 1, 2, in this case 7, right? This number here, the total number.
Oh, okay. I thought that's what it was.
Yeah, I equals 1. Yeah. Okay. So that's all that's saying to do is x sub I, right? And we divide by n. You're just taking 2 plus 6 plus 7 plus 8, right? Plus 9 plus 9 plus 11, right? And you're dividing by 7 there. You got some numbers. Feel better. Now, so that's our x bar from the sample average or mean, right? And now we have, our sample variance. And that one I'm going to take, well, I got to figure out what my average is. So, I don't know if anybody wants to do that. But anyway, so what you would do is you take your average, which is x bar, right? So you're going to summation of every observation minus x bar squared divided by, in this tape, it's divided by n minus 1, which is 6. Oh, I'll just put n minus 1 here. Okay. So over here, this is going to be, it's going to be 2 minus whatever the average is squared plus 6 minus the average squared plus dot right all the way to the last one, which will be what? 11 minus x bar squared, all divided by 6 n minus 1. Is it okay? Now, we have this, so we have a measure of average and we have the spread away from the average, yeah? But if we had, like, this thing was 111, for example, we would call that an outlier. You can see how that's going to mess up your average, right? Because it was a freak, an error, a mistake, or whatever. So we have this other measurement called a median. And the median doesn't depend on addition, it depends on geometry. So you take it, you have to organize the data from smallest to biggest, and then you go physically over to what it would be the midpoint. And so the median is this midpoint. All right. Now, we also call this the second quartile. The median is, in fact, the second quartile on a quartile graph that we're going to do. Okay? So to find the first and the third quartile, you do the same thing, but now you do another thing, but from this side. So your first quartile will be, 6, 8. And your third quartile will be these three. Notice how with this median and this quartile, notice that this thing's not bothering me anymore so much. Right? Because I'm not adding it. I'm just going geometrically down to this point, which is halfway between here and here. Now, if you don't have like an odd number, then you'll have to take the average between, say, 8 and 9 to be in the middle. What? Does anybody understand? Okay. So here's the, they have something called a normal quartile plot, which you won't have to solve, but this is the way to look, another way of looking to see if the data is normal. Okay. Now, if you look at the graph of this quartile, here, oops. Yeah. Okay, this is a quartile graph. So if your observations line up pretty well along this, then this is evidence of a normal curve without even looking at the histogram. Okay? And here's how to solve it. I mean, here's the problems. I mean, we have software. You also have, if you're going to do it by hand, and then this is how you do it with a Texas Instrument. Then the stat disk, we're not using it. Minitab is very popular. Right now we're using this, so it tells us how. I think I showed you how to do a histogram. We'll do another one. Okay? We're starting to get rolling now. And let's see. Let me clear that out. Okay. So we'll do that next. All right. We're really moving along. 54. You can also do it on Excel. They used to be taught with Excel because a lot of people know how to use it. And then there's another option within Excel, an insert that has a macro that does the statistics that you would do on Crunch. So if you're efficient, you can use that. If you don't want to use that Crunch, what's going on? Okay. So anyway, you can see what happens depending if you have these cell widths too fine, then you're having gaps. And it may be that way. I was telling you that when I look at math scores, usually they're like this. Either you understand or you don't. There isn't a bell curve here, or if you want like mini bell curves, it's called bimodal. Math is that way. You can't just go to the next skip and say, okay, I'll do better in the next math class. Not really. I mean, stats is kind of different because I'm doing a lot of hand waving. But yeah, this would be a bimodal distribution. It tells you something. Okay. A relative histogram. And that's the quartile. Okay. This, to me, it's just another frequency graph, isn't it? Instead of writing numbers, you're putting the dots like this. It's still relative, though, because these are frequencies. It's not, I haven't divided it. Stem and leaf, dot. This is the pulse rate of males. The stem and leaf. They're putting how much of each, the numbers as they fall into the category. Stem and leaf. We'll work these out. I'm just right now, we'll go over the homework. This is fatalities. This is a polygon histogram. You just take in each cell and you connect the high points. Okay. Bar graph, Pareto graph. These are just different types of graphs. Pareto, they have, these are categorical, right? Some data is categorical. You don't have numbers to split up. You have comparison of jet ski. I guess this is what's been stolen. What's most likely to be stolen? Is that okay? All right. There's the frequency polygon that we spoke about when you connect the highest of each observation size. Relative frequency polygon, remember you divide by little n. So that what's really changing is just the scale. This is total count, right? But when you divide by the total number of observations, these become like probabilities. Yes or no? Yeah? Okay. Okay, there's Dunkin' Donuts and McDonald's. The reason, why do you think Dunkin' Donuts is faster, especially in this range? Because I think it's pretty easy to pull out a donut and slap it down on a plate. And, guess it depends how many policemen. So here we go. All right. Let's maybe do some homework now. Nausea clinic. Now that's where I want to go. Okay. All right. Some more way of displaying the data as a graph. Scatter plots require at least two variables, Guns and Roses. There. Scatter plot. This is waist circumference versus right here, arm circumference. Most everybody has an arm and a waist. So now you plot each of these. Guess what? All of this is the whole sample. Yes? Now, you see how it's kind of tight? Do you see if you put a line through here? If you put a line through here, you would have a regression, really. You can see how tightly it's grouped. That correlation is R that I was telling you about, from -1 to 1. We say that this is correlated. And it's correlated positive or negative? Positive or negative? I can't tell. Positive. So if it had been clustered this way, it would have had a negative slope, right? Here's something with not much correlation. Okay. Oops. I think I figured it out after a while. Okay. A linear coefficient R. The equation is daunting, so I don't want to, because you have to take each of those observations and subtract the average, and it's a lot of work, and it ends up giving you this thing. So here's the frequency. Now, the problem with R is that if you don't have enough data points, it's kind of weak, right? Because if you only have 2 points, a line will fit perfectly. Right, because it takes 2 lines at least to make 2 points to make a line. So you have to keep that in mind if it's too small, right? And now we have this R correlation was about 0.59. Okay, and then they have this It's called a critical value. I'll explain that later. That'll tell you whether or not R is significant or not. If it's around 50%, it's not so good, really, right? Because it's just saying, yeah, it's like anything is 50%. It's just a flip of a coin. All right. Now, when you have this critical value, which will be calculated for you, it hits, and then this is the range from 0. Remember, it goes from -1 to 1, I told you? Depending whether it's a negative or positive slope. Okay, now you got R. And you have these things called critical values that will be generated, right? If your R statistic, falls in this range over here, right? Then we say, oh, it's significant or not significant, depending on where it's actually falling in. So here's correlation, no correlation. This is pretty high. I mean, it goes, this saying there's a negative or positive correlation. Our cutoff for what we consider to be significant is when it's like 87%. You understand? Either it's landing in here or it's landing in here. If it lands anywhere in here, we say R is not really helping us in any kind of predictive. It's a lot, I know. Okay. How are we doing on time? Are we? You starting to move? Really, I'm having so much fun here. I don't know. Damn. Time flies when you're having fun. Okay. Well, we'll do more homework next time. And we didn't do any, but we'll do more.